Hi, my name is Bahadur Akhmedov. In this video lecture, we are going to discuss about the column spaces of matrices. The column spaces of a matrix is going to help us to understand when the system of linear equations is solvable. So essentially, if you're given a system of linear equations in the form of AX is equal to B, then we're going to define the column space of this coefficient matrix A, and this column space is going to help us to understand when the system of linear equations is solvable. And if the system has no solution, basically is not solvable, it is going to tell us why it is not solvable. So throughout this video lecture, we are going to define what is a column space. But before we do this, I would like to again talk with you about the matrix multiplication. And again, if you've got a matrix A multiplied to the vector X, and this is equal to the B, we can again look to this matrix multiplication AX as a linear combinations of the columns of this matrix A. So essentially, the first column of the matrix A is going to be multiplied to the first element of this vector. And the second column of this matrix A, the second column of this matrix A is going to be multiplied to the second element of this vector. So again, we can look to the matrix multiplication of the A to the X as the linear combinations of the columns of the matrix A. So essentially, you can just look to this as the first column, so it's some vector. So the first column is going to be multiplied to some constant, right? Plus the second column, so the second column, it's a vector, times to the scalar, and this should be equal to some vector. And this vector is going to be equal to the b1 and b2. Okay? And it is really important for us to understand that this multiplication is a linear combination. It helps us to understand the solution of a system of linear equations. So essentially, hey, we are saying that hey, the matrix multiplication A to the X can be written as the linear combinations of the columns of the A. So now let's say you are given some system of linear equations where the coefficient matrix A is given as 1, 2, 2, and 3. So this should be multiplied to the x1 and x2, and this should be equal to the 1 and 2. So our ultimate goal is to solve the system of linear equations. And what does it mean? It means like find this x bar, which is going to satisfy this equation. So when you look to the system in this form, it is probably not so easy to see the solution. But when you write down this matrix multiplication as the linear combinations of the columns of this matrix, you will see the solutions right immediately from there. So let us do this. So I'm going to write down the first column, 1 and 2, so times the x1 plus 2 and 3 should be multiplied to the x2, and the sum should be equal to the right hand side part. So here is a 1 and 2. So you see, so you multiply 1 and 2 to some constant, plus 2 and 3 times to the constant. It should be equal to the 1 and 2. So can you guess what is the value of the x1 and x2 is going to satisfy this? Obviously, x1 should be equal to the 1, and x2 should be equal to the 0. And in this case, you're going to have the solution, right? So what does it mean? It means that you can figure out the solution vector x bar when you are going to multiply the matrix into the vector and look to this as a linear combinations of the columns of this matrix A. So essentially 1, 2, 2, 3 can be multiplied to the vector 1, 0, and this should be equal to the 1 and 2. So you see, so understanding the linear combinations of the columns of the matrix A help us to solve the system of linear equations. So now let's look to the system of linear equations again. So and try to understand when it is solvable. Okay. So we have got the system of linear equations, right? And we can understand. So whenever I say, hey, could you please solve this system? So what you can understand is that, hey, you can understand. So we need to find an x bar so that ax bar is equal to the b. So you can understand this like this, but at the same time, you can understand this question as find a specific linear combination of the columns of this A matrix. So this is the A matrix of the columns of the A matrix, so that this combination is equal to this B vector. So essentially, you need to figure out the two constants, x1 and x2, so that if you combine the columns of this matrix C1 to the x1 plus C2 to the x2, right? And this should be equal to the B1 and B2, okay? And could you please tell me when the system of linear equations is solvable? So this system of linear equations is solvable if such a condition, such a combination exists, okay? So if such a combination exists, if such combination exists, okay? And again, so whenever we ask you to solve a system of linear equations ax is equal to the b, we can understand this question in two different ways. So the one way would be to find this vector x bar, so that if you multiply the a to the x bar, it's going to give you the b. Or you need to find a specific linear combinations of these two columns, C1 and C2, okay? So that this combination is going to be equal to the right-hand side part. So this combination, specific combination, defines you to which constants x1 and x2 you're multiplying the columns of this matrix A. So what I want is, I would like to try to, so let's try to do this in example. So let's say we are given this matrix or the system of linear equations. So the 1, 2, 2, 4 times the x1 and x2 is equal to the 1 and 3. So what you need to do is you need to try to explain the column space of this matrix A. So the column space is essentially all linear combinations of the columns of the matrix A. So we're going to discuss this in a moment. And check the consistency of the AX is equal to the B. Basically, we need to check whether the system of linear equations is solvable. So again, if you are given the system of linear equations and I ask you, hey, could you please solve this? How you can do is, so you can just like plug in this vectors into the Gauss-Jordan elimination algorithm and try to solve this. But now at this stage, what I want is I would like to try to understand whether the system is solvable or not by just understanding the linear combinations of these columns of the matrix A. And again, so if I say, hey, could you please solve the system of linear equations? You can say me that you need to multiply the first column of this matrix, 1, 2, to this specific constant x1, plus 2 and 4 is going to be multiplied to the x2, right? And this should be equal to the 1 and 3. So I'm asking you, hey, give me this linear combination, of these two vectors, so that this is going to be equal to the 1 and 3. So let's look a little bit in details, these two vectors, 1, 2, and 2, 4, and what does it give us, their linear combinations. In order to do this, I would like to draw them. So let's try to draw them in a two-dimensional space. And again, so if you would like to draw 1 and 2, you're going to get this vector, right? Oh, this is 2 and 4, and this is 1 and 2. So this yellow vector is going to be a 1 and 2 vector, right? And the blue vector is going to be here. The blue vector is going to be 2 and 4 vector, okay? So whenever I say, hey, give me a linear combinations of these two vectors, what do I mean is that I just multiply this 1 and 2 vector, this yellow vector, to some constant, and multiply this blue vector to some constant, right? And just add them. Okay, if you just multiply 1 and 2 vector to some constant and 2 and 4 vector to the constant and add them, you are going to always get a vector along this line through these two vectors. right? So any linear combinations of these two vectors is going to be on this line. So let us fix this. Any linear combinations of these two vectors, 1 and 2, 2 and 4, are along this line. Okay? So now let's try to draw this vector 1 and 3. So if you would draw this vector is going to be outside this line, right? And if I say, hey, could you please solve the system of linear equations? And I told you before that we can ask this question, rephrase this question differently. So could you give me the linear combinations of these two columns, 1, 2, and 2, 4? So this is going to be equal to the 1 and 3. You basically tell us that, hey, this doesn't exist, right? Because any linear combinations of these two vectors are going to be along this line. And if you all would like to find a linear combinations which is going to be outside this line, you basically tell that this doesn't exist simply, right? So this system has no solution because this 1, 3 is outside the line. And what we basically say is that, so this line is going to be the column space of the matrix A. Okay, so essentially the column space of the matrix A is all possible linear combinations of the matrix A. And if the right-hand side vector is not in the column space of the A, then the system has no solution. So we can quickly check whether the system has solution or not by just constructing the augmented matrix and by just like simplifying them and by going through the Gauss-Jordan elimination, right? So let's say I've got this matrix, which is the augmented matrix. I copied the coefficient matrix and the right-hand side matrix, and I need to bring this into the reduced row echelon form, and I can do this by eliminating this t, for example. So we can multiply the first row to the minus t, and add this to the second one in order to get a matrix which is going to be equal to the 1, 2, and 1. If you multiply 1 to the minus 2, it's going to be minus 2. If you add this to the 2, it's going to be 0. 2 times to the minus 2 is going to be equal to the minus 4, plus 4 is going to be 0. 1 times to the minus 2 is going to be minus 2, plus 3 is going to be equal to the 1. Okay, and this system, so this reduced row echelon form or the row echelon form tells us that, hey, the system doesn't have a solution, because if you look to the second equation, which is going to be correspondent to, so which corresponds to the following equation. So the 0 times to the x1, right, to this x1, so plus this second 0 times to the x2 times to the x2, and this is equal to the 1. And could you please tell me x1 and x2 which would satisfy this equation? So they don't exist simply, okay? So the system has no solution, and we can explain this by looking to the column space of this matrix A, okay? So the column space of this matrix A is this line, and this right-hand side vector B is going to be outside the column space, so that is why the system has no solution. So now I think we're ready to define what is the column space. So the column space of the matrix A is all possible linear combinations of the columns of A. So we also say that, hey, all possible vectors AX fills the column space, and we are going to denote the column space of the matrix A as the C of A. And again, I would like to describe here, so let's say you are given a matrix, so let's say 1, 2, 2, 3, okay? So all possible linear combinations, so it means that you're going to just multiply this to some vector, x1 and x2, right? So 1 and 2 is going to be multiplied to the x1, plus 2 and 3 is going to be multiplied to the x2, for all values of the x1 and x2 from the real numbers, right, is going to be the column space of this matrix A. So that is why if you look to this matrix multiplication as an AX, so that is why we say that, hey, so all possible vectors AX fills the column space. It means that, hey, all possible vectors means that all possible linear combinations of the columns of the A is the column space. So at the same time, there is a concept, so-called the span of the vector spaces or the vectors. So what we say is that, hey, so let you are given some k vectors from the Rn space. So all of these vectors are n-dimensional vectors. So essentially, each of these vectors, vk, is going to be given as the n-dimensional vector. So it's going to be given as a v1, for example, and so on, vn. So they have n components essentially. So we say that the span of this set of the vectors, v1, v2, and so on, vk, is the set of all linear combinations of the vectors, of these vectors. So this is essentially the mathematical term which is going to be substituted this long expression. So instead of saying that all linear combinations of some vectors, we are going to just substitute this with this word span. So essentially, the span of these vectors is going to be all possible linear combinations, right? So I'm going to multiply the first vector to some constant, the second vector to some constant, and the case vector to some constant. And this is going to include all of the possible values for this constants. And the reason why we're introducing the span of the vectors here is that we would like to essentially define the column spaces of the matrices using the span of the columns of the matrix A. And again, so the column space of the matrix A is all possible linear combinations of the columns of the A, right? And we can simply say that, hey, column space of the A is the span of the columns of the matrix A. So essentially, if your matrix A is given with the two columns, C1 and C2, okay, then the column space of this matrix A is going to be the span of these two columns, C1 and C2. Okay, so this is what does it mean, the span. So let's do one more example in order to try to understand what does it mean, the column space. So in this case, I would like to look to the matrix in 3D. So essentially, the columns of the matrix A are going to be given with the three components. So let's say we are given the two columns of this matrix A, right? So the A matrix is given as C1 and C2. So if you remember, what does it mean? The column space of the matrix A is that the span of these two columns, C1 and C2. Okay, so I'm going to just put this vertical lines to describe you that, hey, they are the vectors. So now, if you are going to define the column space for this matrix, it's going to be all possible linear combinations of these two vectors, essentially. So the 1, 0, 0, and 0, 1, 0, right? So let's try to draw these two vectors. So the 1, 0, 0 is going to be this vector along the x-axis, right? So this is going to be 1, 0, 0. And 0, 1, 0 is going to be this vector along the y-axis. So this is going to be 0, 1, 0. So what does define the all linear combinations of these two vectors is that the plane, right? So we remember that all possible linear combinations of the one vector is going to define the line, and all linear combinations of the two vectors are going to define the plane. So this essentially the span of the columns of this matrix A is this plane, the xy plane. And if I would like to solve a system of linear equations, essentially with this matrix in the form of AX is equal to the B, and let's say this B is going to be the vector, let's say 1, 1, and 1. So let's say it's going to be 1, 1, and 1. So essentially, it's going to tell me that, hey, the system doesn't have a solution, right? So because 1, 1, 1 vector is going to be somewhere here, okay? So like this vector. So this is going to be 1, 1, 1 vector. And you see, so this vector is outside the plane. So no matter how you're going to combine these two vectors on the xy plane, you will never reach that green vector, right? So you cannot get out from the plane. So that is why the system has no solution. So this is essentially what is the column space, and this is essentially how we can understand the solvability of the system of linear equations by constructing and describing the column spaces of the matrix A. Thank you very much for your attention. I hope that this video was helpful for you.